Very good evening and welcome to lecture number 4. And I'm extremely sorry those who have watched my earlier lecture 4. There was an audio problem, so I am again doing this live streaming because I understand the problem was that as soon as I'm removing myself and showing the entire slide, there is actually a problem with the audio. So welcome to lecture number 4 of quantum field theory. Now, those who have seen my lecture earlier, part 1, part 2, and part 3, you have seen that these lectures were primarily started with the history of quantum field theory, why quantum field theory is required, what is the need of quantum field theory. Without quantum field theory, what were the problems? Quantum electrodynamics, quantum chromodynamics, the quarks, the leptons. Most importantly, we have dealt with Schrodinger's equation, the classical limitation of Schrodinger's equation. Thank you to Sushil Gunratne, who really appreciated my derivation of the Schrodinger equation. It actually showed that why Schrodinger's equation is unable to show the spontaneous emission, the limitations as the radius of a spherical mass of electrically charged goes to infinity, and different other things. So in today's video, today's lecture, I would be explaining a little bit upon the what we call are the limitations of the standard model. Now, if you go back to my previous videos, these are the slides where I have explained basically the standard model, which explains everything, starting from the elementary particles to quarks, the up quark, down quark, charms, protons, bosons, everything. Although standard model, quarks, leptons, etc., they actually define and make understand of all the other forces. So in this case, I would say there are still certain limitations of the standard model, which I would definitely like to explain in today's lecture. So first of all, let us understand what are the limitations of the standard model. And in this case, I would say the basic first limitation is what is called is a free parameter. Now, first of all, what I would like to explain to you is that what is actually a free parameter. Now, say, for example, in case of defining a particular mathematical model, we sometimes do certain things. We can make a model which can be which can be measured experimentally. Okay. Say, for example, we want to develop a motion of a projectile. So we start with certain assumptions, right? The projectile, such as that it is moving in a vacuum, it has got a velocity, there are other forces like gravity, etc. And then you can use these assumptions to write down a set of equations that describes the motion of the projectile. Now, these equations, whatever x, y, z, etc., whatever it will happen, will contain some unknown quantities, and such as initial velocity of the projectile, its mass, etc. Now, these unknown qualities are basically what are called free parameters. Okay, so to determine the values of the free parameters, what we need to do? We need to do an experiment. So, for example, to measure the initial velocity of the projectile which is being fired from a gun and measuring its speed with the radar, etc. So once we determine the values, that means the equation which contains those unknown quantities and the free parameters, then obviously the mathematical or the theoretical model of the projectile or whatsoever can be given any set of initial conditions. So free parameters are essentially tools for developing and testing physical models, and it is important to be aware that free parameters it has got certain amount of limitations. Okay, let me go back to my slide now, and things would be easier now. So here you see some people say that there are 19, some people say there are 16 for free parameters. Doesn't matter, but what matters is that these free parameters provides a kind of a limitation for the standard model. First of all, as you can see that in case of a free parameter, especially the neutrinos, they have a mass. If you have attended to my earlier, YouTube live with Dr. Jessica, who has exclusively spoken about neutrinos, that neutrinos do have a mass, etc. So neutrinos do have a mass, but the problem is that the standard model doesn't yet define what is that neutrino's mass. Although experiments, as I told you, shows that neutrinos do not have a mass. So standard model predicts that neutrinos should be massless, but experiments have shown that they do have a mass. So here is a contradiction. Standard model shows that there should be massless, but experiment shows that neutrinos do have a mass. So the free parameters are not properly defined, and that is basically a problem with the standard model. Also, let us remember that the standard model does not include gravity. So gravity is one of the four fundamental forces, and standard model does not include gravity, which we are still starting. Standard model also does not include the definition or explanation of dark matter and dark energy. And we know there are a lot of researches in cosmology, etc., going on in dark matter and dark energy, which makes up 95% of the universe, but the standard model does not provide anything. So it does not include gravity, it does not include free parameters, it does not explain dark energy, and as I told you that it should be massless, but it should define that doesn't have a mass. So, but what I would say that despite all its, kind of a limitations, etc., a standard model in particle physics is something which will accurately describe a wide range of experimental data. However, it is clear that the standard model is definitely not a complete theory, and we need a new physics or a new model in which these neutrinos, massless parameters, etc., can be defined using the standard model. Okay, so having laid this kind of a definition, I would come to what is called the fundamental interaction. Fundamental reaction in the sense that all the major forces of nature, whatever that we are dealing with, can be explained with these fundamental forces. Uh, okay, just let me check in whether my audio, I think, is now working nice. If somebody is watching, can you just put it in the comment box that whether the audio part is now the audio is going nice and fine? Okay, in the chat box, if you can just put it to me. Right. Okay, so what we see from here particularly is that these are the four forces of nature. So we see that gravitation and electromagnetic interactions, which produces significantly, I would say, long range of forces whose effects can be definitely seen in everyday life, right? So you see the gravitational forces, the curvature of space-time, it happens, and it has got a long distance. Electromagnetic force also happens with a kind of a field, as I've shown in the slides. The strong forces, these are the subatomic particles, and the weak forces also. So each of these known fundamental interactions can be described mathematically as a field. This is very important. Each of these fundamental interactions can be described mathematically, which is called a field, and the gravitational force as attributed to the curvature of space-time is described in Einstein's general relativity. The three other discrete quantum fields and their interactions are mediated by the elementary particles and defined in the standard model. And now we are going to see that what are those particles and how do they interact in the next part. So here you can see that the the interaction that the weak force, the strong force, the electromagnetic, and the gravity. So these are the mediators, W and Z bosons, the gluons, the protons, and the gravitons. So these are the electroweak theory, quantum chromodynamics, quantum electrodynamics, and general relativity, or the string theory, which is being taught. Now, in terms of gravity to be taken as weak force, here I have got a point to make. Now, considering, say, for example, this is a bottle and this is a mobile. So in case we are bringing things together to each other, you will see nothing is nothing is happening. Still, this is a big mass and this is a big mass. We are bringing things together, but nothing is happening. But in case of a electromagnetic or a weak force, if you bring things together, it causes a problem. It causes a kind of a reaction. So what is more important that you need to understand that gravitational force, it is called weak also for another reason, that in order to measure the curvature of space-time, we require a huge mass. We require a mass which is as large and as huge as a Jupiter. We require mass as large as a supermassive black hole or something like that. That means it is weak in terms of what? In terms that only when we get such a huge mass, then only gravity or Einstein's field equations will be able to define the space-time curvature. Otherwise not. So this is one of the aspects of calling gravity as a weak force. So there's a strong force, there's electromagnetic force, and there is gravity. So taken all these things together, these are actually the fundamental reactions. So the fundamental reactions are very fundamental, which explains everything related to gravity. Okay, so we go from here and we try to understand what is a weak force. So here you can see that weak force is basically, there are two types. One is the interaction between subatomic particles that is responsible for radioactive decay. And it is also, weak force is something which is responsible for nuclear fusion and nuclear fission. Now, here is one thing you need to understand. Radioactive decay, which is also known as nuclear decay or radioactive disintegration, this is the process by which an unstable, I would say, atomic nuclei loses energy by radiation. It loses energy by radiation. So strong and weak force is loose, it radiates, and it gives radioactive decay. Now, there are three types of decay, as I have pointed out in the slide. As you can see, alpha decay, beta decay, gamma decay. I will come to those decays later. But remember that the weak force is the mechanism that is responsible for for the beta decay. So there are other two forces which are governed by electromagnetism and nuclear force. And there is, some people feel that there is a fourth type of force which is called, which causes an electron capture, in which basically an atom's nucleus and an inner electron, emits from the electron shells. So alpha, beta decay, and gamma decay, I will come to that part later, but it basically emits a alpha particle, transforms it into an atomic nucleus. It emits a beta particle responsible for weak force and forms a electromagnetic electron, and it's short at wavelength. So this is basically what we call is a weak force. Now you might be wondering that these are very fundamental in terms of particle physics, but why I am teaching those things? This is important because we need to understand that until we understand the basics, the particles in motion, their characteristics, behavior, etc., when we move into the Lagrangian and the difficult part of mathematics, things will be much more difficult. So that is how we make up things. So from here, you see there is a concept which should be cleared up. That is, what is a nuclear fusion and a nuclear fission. So very simple, fission is somewhere an atom splits up into smaller nuclei, and fusion is a reaction which two or more atom nuclei are combined to form one or more different atomic nuclei. So fission is where it actually splits up, and nuclear fusion is taking to it. That is why we call all those fusion music and fusion foods, because we are bringing things together, right? We are bringing things together. That is why we call it as a fusion, and fission is basically decaying of those particles. So this is being discovered by Otto Hahn in 1938, and this is an important fusion because the nuclear fusion actually happens in stellar nucleosynthesis in terms of stars, etc. So do have a clear understanding of a fusion and a fission. So fission is something which breaks up into smaller nuclei, and fusion is something which brings things together. Okay, here is something very important. So it was Enrico Fermi or Fermi interaction, which is an explanation of the beta decay. So remember that it was Enrico Fermi who first proposed the electroweak theory, although later it was united by Abdus Salam Stephen Weinberg model, but it acted as a kind of a precursor to the fundamental reaction. So Enrico Fermi's interaction is an explanation of the beta decay, which was first proposed around 1931 by Enrico Fermi. The theory actually posits that four fermions directly interact with each other. And Fermi was the first to introduce this coupling in his description of beta decay, right? Just hold on for a second. Right, so this was that, and later, as you can see, these three gentlemen, Abdus Salam, Stephen Weinberg, and Sheldon Glashow, actually united this, and it was awarded Nobel Prize in 1979, and for their contributions to the unification of the weak and electromagnetic interaction of elementary particle, which is known as the Weinberg-Salam model. So this was the first unification it was done, but let us remember, prior to this interaction of this theory, it was Enrico Fermi who first proposed the electroweak theory, and it was through Fermi interaction that the beta decay comes into play. And now if you go back to this slide, you can see here weak force actually is responsible for the radioactive decay, and this radioactive decay consists of three particles, alpha, beta, and gamma, and this beta decay was already proposed by Enrico Fermi, and later it was united by Stephen Weinberg's Salam model. Okay, here is a kind of a summary of what is called the weak force or the weak interaction. So in weak interaction, as you can see, fermions can exchange three types of forces. So weak force is basically taking place with exchange with three types of forces. One is W plus, W minus, and Z bosons. So the masses of these bosons obviously are far, far greater than the mass of the proton and neutron. Obviously, proton and neutron do have a mass, but the masses of these bosons are far greater. Now, in fact, the term actually we called weak, it is because its field strengths are over any set of distance is typically several orders of magnitude less than that of electromagnetic force. So if you consider the electromagnetic force to be at a certain distance, it is much lesser. So that is why we call it as a weak force. So the I would say the higher masses limit the range of the weak interaction. By contrast, you can say if you take a photon, which is the force carrier of the electromagnetic force, it has got zero mass, consistent with infinite range of electromagnetism. And we have in search of the graviton hypothetical, which is expected to have a zero mass. So here you can see W plus, which has got either a positive or a negative spin one, has magnetic, etc. And I've just given the giga electron volt, the values. The photon is massless. It has got infinite range. It can travel up to anything. Z0 bosons are electrically neutral. They have a spin 1, right? Remember, these are a spin 1. This has also got a spin 1, and W minus also got a spin 1. So that means these weak forces, because they have got spin 1, that means they are a fermion. Remember, if you go back to my previous class, I mean to say, if you go back to my previous classes, I have explained the integer, positive integer bosons, and then the fermions, etc., which has a spin half, which have a spin minus. So all these are very important to understand. Now you can see that the weak force is basically interacting with that of the with the W plus, W minus, and Z0, and each of them has got a positive integer spin, that is a spin 1. Okay, now we come to which is known as the strong force. Remember, strong force and weak force, it is very simple. The weak force actually is responsible for the decay. So it is the alpha, beta, and the gamma particle, which is decay. And strong will be called a strong bonding. We have friendship between us. So strong force are those which are keeping the atoms binded together. Okay. So the strong force, as you can see, it binds fundamental particles of matter together and they form up what we call the nucleon. So the strong interaction or strong force confines quarks into proton, neutron, and hadron formation. If you go back again to my previous classes yesterday also, I draw it on Sideboard, a kind of a hierarchical diagram, that this you have the quarks, the leptons, and then they form the hadrons. Then hadrons are the higher particles, then they're forming the human body, etc., matter, everything. So that is how it goes. Now, remember that on a larger scale, for about 1 to 3 femtometer, if I consider, it is a force carried by mesons that binds protons and neutrons together to form the nucleus of an atom. So the nucleus of the atom is formed by finding the forces. The most important, what is important is that confines quarks into protons and other hadrons and particles. So that's it. So the strong force inherently we can call has such a higher strength that hadrons bound by this strong force can found new massive particles. These massive particles actually produces mass, gives higher area, and thereby you can say that it forms up the matter. Okay, so this is a kind of a quick definition of what is a strong force. Yeah, I mean to say it is quite simple. You can just go through that. It binds fundamental particles together. It is 100 times than the electromagnetic force, 10 to the power so much times greater than force 10 to the power 38 times than that of the gravitation. So the force carrier or the particle of the strong interaction is basically the gluon or the massless bosons. Okay, and next I go to this part, which is okay, I'm so sorry. I think I have missed one slide. No, this is fine. Right. So this actually, determines a kind of a summary of what it is actually. The photon, which has got mass 0, then we have gluons. Those are the strong nuclear force. Then we have W and Z bosons, which is spin 1 particle. And then now you can see that we have actually explained the standard model, which is the quarks, the leptons, the photons, the Z bosons, gluons, and so on. and decay bosons. So strong and the weak force together. So this actually completes one part of our lesson. I mean to say, starting from the strong force, the fundamental reactions, the weak force, the limitations of the standard model. And if you go back previously, I have covered the standard models, the fermions, bosons, etc. So in the next lesson, what we are going to do is that I'm going to present some more mathematical ideas, starting with the Lagrangians, which are a very central part of, I would say, quantum field theory, any form of physics. And I'm starting up a new series of lessons on what is called general theory of relativity, which would be also a part of this lesson. And it won't be like videos which I make. It will be more mathematical in nature. It will contain equations and going deep into the complexities of tensors, etc. So I will start up. I will try to come live tomorrow, but I'm not sure. Maybe if it is not tomorrow, for sure from Monday, another lesson on quantum field theory. I will quickly brush up and make a kind of an easy understanding of what are the things that we have learned, starting from the basic to today. And then we will start with the mathematics, starting with the Lagrangian formulation, taking the standing waves, complex plane waves, things like that. So this is a re-recording, because live streaming, I mean to say, because the last video had problems with the audio. I'm so sorry, my kind apologies. And I think this video is quite good enough. You can hear my audio, video, and everything. So next lesson again on quantum field theory, with a new lesson coming up on general theory of relativity, more on the mathematical and the real mathematics, explaining general theory of relativity right from the beginning. Thank you very much for coming to this live stream, and to let me know how it was and how things are going in the comment box. Thank you. A very good evening, and wish you a very happy weekend. More lessons to come in physics for students. Stay tuned, subscribe to my channel, do share my videos. Thank you very much.